Okay, we're in section 13.1. The derivative of these vector functions. There's some rules for differentiation. The derivative of the sum of the derivatives. If you have a scaled vector function, you can pull the scalar out and take the derivative of the vector function. Now this one's kind of strange here. There's scalar multiplication by a number, and there's scalar multiplication by a function. That's the difference between 2 and 3. 2 has a scalar number, c, multiplied by the vector function, and 3 has a scalar function, f of t, multiplied by the vector function. And so when it comes time to take a derivative of such a product, then we have to consider the product rule, where we take the derivative of the derivative of the scalar function times the vector function plus the scalar function times the derivative of the vector function. So we have to employ the product rule when we multiply a scalar function times a vector function. So I want to take some polynomial in t and multiply it by the vector. That's scaling the vector for a given value of t. It'll be a number times that vector. And so it's something that we can take the derivative of with respect to t. If it's just a number times a vector function, 7 times some vector function, then its derivative will be that same number 7 times the derivative of the vector function. So that's how it works. And for dot and cross, it's going to be the same thing. If I take two vector functions and dot them, now I use the product rule. If I take two vector functions and cross them and then try to take the derivative of that, I get the product rule again. And I keep the same product. So if I'm using the dot, then when I do the product rule, I have dot. If I'm using the cross, then when I do the product rule, I use cross. So 3, 4, and 5 are all product rule, just different types of product. Scalar function times a vector function, dot product between two vector functions, and cross product between two vector functions. Okay. And we can use these to help us prove certain properties about these functions. And finally, chain rule. If you have a scalar function, basically replacing the variable t, I guess the dummy variable w, every place you would see a w, you see this entire function f of t, then you can just do the chain rule where you take the derivative of the vector function and you evaluate it at that scalar function, but don't forget you're not done there. You should then multiply by the derivative of the vector function. I really think the order on here should be switched. But generally, when we write scalar functions next to vector functions, we put the scalar functions first for whatever reason. So everything that we've done before basically holds, and it's these ideas that can help us understand certain aspects about these. How we're using these properties to prove things, not deriving them or using them to derive other things, but just certain properties about vector functions we can prove. Here's one. If my vector function r of t, which is to represent my position curve, if my vector function has a constant magnitude, then it will be true that the velocity vector will be orthogonal to the position vector. It's a true statement. Okay? And we're going to prove it. All we know is that the magnitude of the position vector is a constant. And so we're going to take that aspect. And also at the same time, sometimes when you're trying to prove something, you don't know where to go. You start on one side, you work it for a certain while, start on the end, work it backwards, and hopefully to have a meet in the middle. And so we're going to start from the known hypothesis that we're going to assume, yes, that our magnitude of our vector function, our position function, is a constant. An example of this would be that helix. The helix function is an example of this. We have the helix function where we have sine and cosine in two of the components and t in the third component. It doesn't have to be I, j, and k in that order, but here it is. Cosine t, sine t, and t. This is the helix r of t. And if you do the magnitude of that, you'll have cosine squared plus sine squared is 1, and then plus t squared, and then you take the square root of that. So that is not something that has a constant magnitude. But if I put constants on there, it's possible I can make it have a constant magnitude. I guess I'd have to put take this t out, I'm sorry, and put a constant in here. Yeah, if I have, instead of this, take this t out and say put a 5 in here, then this will have a constant magnitude. It'll be cosine squared plus sine squared, which is 1, and then 5 squared, which is 25. The magnitude of r of t will be the root of 26, a constant c. This function, what is it? It's a circle, 5 units up from the xy plane, the unit circle. It traverses you around the unit circle for values of t. And it will be true that for that particular vector function, its velocity vector will be orthogonal to its position vector, always. If you think about it, it's just a traversing around a circle, so the velocity vector will always come off tangent to the circle, and there'll be the position vector and the velocity vector. You give me a time t, and my position and velocity vector will be orthogonal. And so let's take at what that means. If you have something that is a constant, then its derivative is 0. Okay? If you have something that's a constant, its derivative is 0. Okay? Now let's take a closer look at what that means. The magnitude of the position, or magnitude of anything, is the dot product of itself, or dot product with itself, and then you take a square root. Basically, we use the other version of this, that the magnitude squared is the dot product with itself. So the magnitude squared is the dot product with itself, so we can take the square root and say that the magnitude of it is the square root of the dot product. And we're going to use the properties that we have on the last slide to help us see what that means. I'd like to be able to take the derivative of this, and I'm sure that it's 0. Okay? I'm sure that it's 0 because it itself is a constant, so it should have a 0 derivative. Okay? It's a function, square root, and inside of that function is a dot product. Okay? So let's work this out. What does it mean to take this guy and dot it with itself and then raise it to the 1/2 power? It would be basically take the dot product to the 1/2 power, bring down the 1/2, take the dot product to the -1/2, chain rule, power rule, and now chain rule. So, okay, you're not done there. You can't just stop. The last slide we saw that we need to then multiply by the derivative of the inside, the derivative of this dot product. Okay, and on the last slide also we saw how to take the derivative of a dot product. The derivative of a dot product, we'll take it using the product rule, where we take the derivative of one, leave the other alone, put a plus sign, and then take the derivative of the other guy and leave the first one alone. And so that's what that is there. I don't really care that you memorize the numbers. I don't want you to do that. Go back to what this first part is. You know, if you take the derivative of square root of anything, it's 1/2 square roots of that same thing. So that's what this is, the simplified version of that. But this itself is back to the original. That's the magnitude of the vector. And so here's what we're looking at. 1 divided by 2 times the magnitude of the vector, and then this whole product rule here. But there's no difference. I mean, these are really the same thing. There's 2 of them. We can combine them together. There's 2 of them. And so this 2, from the fact that there's 2 of these, can cancel with the 2 from the 1/2 power. And here's what we're looking at. The actual derivative of that magnitude function is equal to the dot product divided by the magnitude. If I'm sure that this thing is 0, which I am because it's a constant, then this fraction should be 0. This is just a representation of what all of this is. The dot product in the numerator between the velocity vector and the position vector divided by the magnitude of the position vector. I'm sure that that is 0. We had to go through all this work to get a representation of what that derivative is. Now we have it. How could that possibly be 0? It's only 0 if the numerator is 0. We know that the denominator is not 0. But we're going to say that, you know, our magnitude of our position vector is not going to be 0. We shouldn't have to worry about that. And so if this is 0, it's going to be true because the dot product is 0. And what does it mean for the dot product to be 0? It means that they are orthogonal. Okay, so you kind of work your way from the right-hand side all the way through, work your way from the left-hand side all the way through to the right-hand side, just assuming this and the consequence of it, and then seeing what that means. Sort of deductive reasoning. Okay, it took a while to work through it, but that's it. So that's a true fact. Only going to be the case if your magnitude of your position vector is a constant, and that's rare. But we'll end up using this later. The only reason why I bring it up now is because we're going to need it later on, and so I bring it up now, and I'll come back and say, remember that thing we proved in section 13.1. Here, then now let's use it to talk about something else. Okay. All right, great. Let's prove something else here. Wait, I guess here it is for that one. So the magnitude is not constant for that one. Remember how I had the t there, and I said it's 1 plus t squared? The magnitude isn't constant there. But had I changed the t to some constant, then I would have a constant magnitude. I guess that's what I was getting at there. Don't think that all vectors have this constant magnitude. Here's the helix that doesn't have it. But if you do the same kind of action that the helix is doing all on one level, if you keep the t equal to a constant, then you will have constant magnitude. One more thing I want to prove. If I take the derivative of a cross product, not just any cross product, I'll take the velocity vector cross with the position vector. Instead of working through what that would be, actually finding the velocity and taking a cross product between velocity and position, instead of doing that, I can trade that in for the position vector crossed with the acceleration vector, right? Double prime is the acceleration vector. And I think this ends up being used later on also. And so the derivative of the cross product between velocity and position is the same as the cross product between acceleration and position, but order matters on how you do it. So position cross velocity, when you want to take the derivative of that for whatever reason, you can trade that in for position cross acceleration. That's what this says. Position cross velocity, if you want to take the derivative of it, trade it in instead for position cross acceleration. Okay. If for whatever reason you wanted to do that. Well, let's see why that would be true. Let's deal with the left-hand side. Derivative of a cross product is using the product rule. Take the derivative of the first times the second, cross the second, plus the first times cross with the derivative of the second. So we're just dealing with this guy here and using the product rule on it. Derivative of the first, cross with the second, plus the first, cross with the derivative of the second. But you see the first term there is the velocity cross velocity. Anytime you cross a vector with itself, what happens? You get 0. Okay? So, wait 1 second. Okay, but anytime you cross a vector with itself, you get 0. So that's exactly what we're trying to prove. The second part of that sum is what we need. And so position cross acceleration is the same as taking the derivative of position crossed with velocity. Okay, and the last thing from 13.1 that we want is to look at what happens. What's the geometry behind? How does this look? If I have a space curve and I want to take the derivative, what does it look like? Back when you first learned derivatives, you said, well, if I take the limit of the secant line slopes, I'll get the tangent line slope. Same thing here. Take 2 points on your curve, connect them with a vector this time instead of a line, and I get a secant vector, and it has a certain direction. It's the difference of those two. Think about the parallelogram addition. It's the difference of those two vectors in that order. So R of t takes me to the point P, and I let time change by some small amount h. So I go from time t to time t plus h. I end up further along the curve at some other point Q, and then I have my position vector there. So the blue is my position vector when I'm at P, and the brown is my position vector when I'm at Q. I call the one R of t I call the other r of t plus h. The vector that connects them, I'll call it a secant vector. It's not a tangent vector, it's a secant vector, and it's the subtraction of those two vectors. I'm interested in the tangent vector. I'm interested in what the derivative vector would look like. And so, just like I did for Calc 1, now I'm going to do for this, where I want to scale the vector. So I have this position vector above. I want to either make it longer or shorter, depending on the value of h. And so I divide by h. I scale it by 1 over h. Okay? I still get the secant vector. But as I let h go to 0, then the 2 points will get closer and closer to each other, and I end up with the tangent vector. This is in purple here, I think. The limit, as h goes, this is the official definition of the tangent vector, but we won't correspond it like this. We'll be using our derivative. We'll be using our derivative shortcuts to find derivatives. We won't be finding velocity vectors by this limit definition, but you should at least see it. And so that's why the limit of the secant vectors ends up at the tangent vector as you let the time that is elapsed go to 0, as you let h go to 0. Questions about that? Looks familiar? And finally, sometimes we actually want this tangent vector, this velocity vector, sometimes we want this to be a unit vector. And so if you ever see the variable capital T, then that is the tangent vector turned into a unit vector. So divided by the speed. You take velocity and you divide it by speed to make it a unit vector. You can take any vector and turn it into a unit vector by dividing by its magnitude. And remember that the magnitude of velocity is speed. And so we'll be using this later. If you ever see capital T, we'll refer back to what capital T really is. And here it is, r prime of t over mag of r prime of t. Velocity over speed. And it's a unit vector. It's weird how our book handles this, but they deal all with the derivatives in 13.1, and then in 13.2 they deal all with integrals. So we looked at taking the limit of vector functions and taking the derivative of vector functions, and then in 13.2, although it won't actually hold any weight as much as the derivative and limit do, there is a such thing as taking the derivative, taking the integral of a vector function. Just like those guys' limits and derivatives were component-wise, the integral is going to be component-wise. It's just not as usable. We don't use it in many applications at all. Integrating an actual vector function. We're going to see that when we integrate speed, the magnitude of velocity, we actually get something that's called arc length. But for now, though, integrating just the vector function itself is just integrating component-wise, and it really isn't used for much. Here's an example. So you just have to remember your techniques of integration. The first one will just be the power rule in reverse. For the second one, you need a clever U substitution. And for the third one, you're going to need integration by parts. Okay. All the other techniques of integration you learned in Math 104 or BC Calculus, we're going to say we're not going to use in this class. Partial fraction decomposition, using trig substitution, or dealing with major powers of trig other than squared. We're not going to deal with those techniques. So we'll deal with these basic techniques of just basic integration, using the power rule in reverse. Now here we need a clever U sub. Well, you would think, let U be t minus 1. Whenever the power inside matches the power outside, then you could do U substitution. But when it comes time to sub back for t dt, you're going to have to use this substitution to figure out what t is. So yes, U is going to be t minus 1, and du is going to be dt. Go back to the substitution to solve for t, and see that t is u plus 1. So when you go to substitute for t, you put u plus 1, and you'll be looking at u plus 1 times the square root of u. And for this particular one, we'll do a limit switch and say that when t is 2, we get u to be 1, and when t is 1, we get u to be 0. So our upper limit is 1 and our lower limit is 0. And we can integrate that. We just have to distribute the square root across. This always happens when you have a binomial to some power, and you have the same the same power of the binomial on the outside. This strange u substitution can work for you. And so we distribute the root across, and we have u root u, which is u to the 3/2, and then we add to that u to the 1/2. So we get u to the 5/2 and 2/5 of that, and u to the 3/2 and 2/3 of that, and we just put a 1 in. And we're just adding 2/5 and 2/3, getting 6 and 10 15ths. So a grand total of 16 15ths. Now I want you to see a weird u sub. I'm sure that you're familiar with just regular u sub. I just wanted to show you that sometimes the u sub can be strange when the powers match like this. Most time when you do u sub, the power inside is one more than the power outside, and it comes forth straightforward. This is not so straightforward. I just want you to see it. And then finally, the last one is integration by parts. But when you have a polynomial times a trig, I want you to see that there's a shortcut. It's called the tabular method. Okay, you can just do regular u substitute integration by parts, where you let u be the polynomial part and dv be the trig part, and you work it out. At the end, I'll show you that you could do this by a substitution, by a shortcut. It doesn't really helpful. The shortcut isn't helpful unless the power on t is something more than 1. So since it's not, let's just work through the regular version of integration by parts. I take the derivative of the u. I take the integral of the dv. Remember, when you're integrating sine of some constant times t, you get 1 over that constant. And then what function has sine as its derivative? It's negative cosine. And then what is integration by parts formula? It's uv minus the integral of v du. And it's supposed to be a better integral, and it is. It no longer has the t on it anymore. The uv is not integrated at all. It's just evaluated. And then the new integral doesn't have a t anymore. And so it turns out that you traded it in for 1 over pi times the cosine of pi t. What function has cosine pi t is its derivative? Sine pi t, not enough. You have another 1 over pi that comes in, so that becomes 1 over pi squared. Instead of evaluating the outside and then later evaluating the integral, I just put it all together and evaluate them. I got to put a 2 in for t and then put a 1 in for t. So cosine of 2 pi and sine of 2 pi, and then cosine of pi and sine of pi. Okay, well the cosine of 2 pi is the same as cosine of 0. That's a 1. And the sine of 2 pi is 0. Sine of pi is 0. Cosine of pi is negative 1. So you end up with negative 2 over pi, and then to that, you're going to add 1 over pi. You're going to take away, I'm sorry, 3 negatives there. I didn't see that. 3 negatives. 1 negative from integration, 1 negative from the u substitution, and a 3rd negative from evaluating. 3 negatives there, I'm sorry. So negative 2 over pi minus another 1 over pi gave us this answer here. But we could have done it with the shortcut. So if you want to YouTube search or Google search the tabular method or table method for integration by parts, there's a way you could do that. It's really helpful when your power on the polynomial part is anything 2 or above, because that would require integration by parts twice or higher. Tabular method for integration by parts. Find a video on that. And it's only usable when you have a polynomial times sine or cosine, or a polynomial times an exponential. It saves you a lot of work. I'm not saying that I use it here, but yeah, you should see it. If you go to my 104 page, I just covered that in my 104 class. You'll see the lecture for integration by parts, and if you skip through, you'll find me using the shortcut. So either YouTube search it or go to my 104 page, and you'll see an example of that. And that's the extent of your integration knowledge that I expect you to bring into this class. Okay, but the problem is that when you get this in the end, it's not an object that we use. It's a vector, yes, but what does it mean? We can't really say much about that, unfortunately. But it's in section 13.2 for whatever reason. Along with something very strange, it goes and talks about projectile motion. So it changes from this into that. I guess, you know, when you integrate acceleration, you should get velocity. And when you integrate velocity, you should get position working backwards. And so, I mean, I guess it makes sense. But here we talk about projectile motion. And those of you who had physics, you're going to just use your physics formula. I'm going to first teach it as if you don't know any physics at all. So we're going to have this projectile launched from a certain height and have a certain mass, launched at a certain angle maybe, or somehow I know the force of which is its initial force, that it's the initial velocity, and I can find out many aspects about the whole motion. In fact, when I make some assumptions, I can actually get a vector that will tell me, you know, the space curve that's traced out by the projectile. Of course, I have to assume some things about gravity, and because the force due to gravity is minus mg in the j direction, and the Newton's second law is ma, I can use these things to see that the mass cancels out. And so, when I have this projectile motion, the only we're going to say that everything else is negligible, no air resistance, and so the only forces acting on the projectile is the constant. That's a universal constant for gravity. It depends on whether you're in feet or in meters. If you're in feet, g is 32 feet per second. But if you're in meters, then I'm sorry, what is it? I'm sorry, feet per second squared. Sorry. And if you're in meters, it's 9.8 meters per second squared. And so it depends on how it comes at you. Anyway, and it's acting in the j direction down, negative g in the j direction. And that's where we start at. We integrate that to get velocity. We integrate that to get position. Okay? Acting like we know no physics at all other than these basic physics laws. Okay? So we're going to integrate acceleration. And what we get is minus gt plus a constant. But see, our constant isn't like just a scalar constant. Our constant is a vector constant. So that's a bold. I don't know if you can see it, but it's bolded. Okay. So my minus gt is in the j direction, and I get this constant c1. The way I can figure out what that constant is I can plug in t equals 0. I'll save that, though. Let's integrate again to get position, right? When you integrate velocity, you get position. And so I take that guy and I integrate it, and that's how I'll get my minus g t squared over 2. My constant c1 will be times t, and then I get another constant vector, call it c2. And it's going to be my job to figure out exactly what these are. Go back to the velocity function and set t equal to 0. You'll have an initial velocity of your projectile. Call it v sub 0. But back in the formula, if you plug in t equals 0, that gives you exactly what c1 is. So c1 is your initial velocity. The initial velocity vector, v sub 0, v naught. Do the same thing for the position vector. Plug t equals 0 into that. So we already know now that c1 isn't a mystery anymore. We now know that c1 is exactly v naught. So let's go back and plug in v naught for c1. And this is our position vector. And so we'll plug in 0 to that and say that, okay, it's not launched from the ground. It's launched from some initial height. So there's initial position r naught. Call that height h or something. We'll call later. And so then when we plug 0 to that, these guys go away. T is 0. T is 0. These guys go away, and that gives us what c2 is. So here's the vector that represents position. It's in a strange form, but we'll take it. Here's the vector that represents velocity. Still in this strange kind of ijk, you know, not in the form that we want. And we're going to say, okay, starting with this, if we know some things about v, if we know what v naught is, maybe the angle that the projectile is launched at, maybe we don't know exactly what v naught is. We know the force v naught, the magnitude of it, maybe. Maybe we'll know the angle that the projectile is launched at. And then for r naught, maybe we know how high off the ground it's launched from. Then that should be enough for me to come up with actual vectors to represent the motion. And the motion we're assuming is acting on, you know, this linear path, and it has this sort of height. We can measure things about it. We can know what's the largest height reached, where will it hit the ground, or maybe there's some wall, where would it hit the wall. There's lots of questions that we can answer based on that motion once we know a vector formula for the motion, once we know the vector function. Okay? So let's go into the IJK or V brace notation and say we know the initial height, call it h, the initial speed is the magnitude of V naught, and then the initial angle, theta, in radians. Okay? So we can take V naught and break it to its components. We have V naught cosine theta and V naught sine theta. You guys know that. That's how you do your force. So that's what V naught's going to be in I and J. Great. And the magnitude of V naught is the initial speed, right? Magnitude of velocity is speed. So this is the initial speed. T is 0. Take that and plug it in. Knowing that A is minus G, we can say that A is 0 minus G in V brace notation. Knowing that V is minus GT times in the J direction plus this initial velocity V naught, we can add these component-wise and end up with the component version of velocity. And only the J component has this minus GT subtracted from it. And then putting that all together with the position, our goal is to get a nice V brace notation for the position function. It describes all the motion. And so we're going to say that when we have this initial vector r naught, well, it's 0 in the I direction, and it's some h initial height in the j direction. So we plug in V naught, we plug in r, and then we take these three vectors and add them together. Remember now that V naught is multiplied by t. It wasn't before, of course, but when we integrate it is. Okay, and we add these three vectors component-wise, so i's with i's and j's with j's, and we end up with a nice formula for the motion in V brace notation, where this represents the motion in the I direction, and then all of this represents the motion in the j direction. And that can help you answer questions. Typical question is you got, the projectile is a baseball, and you have the person hitting it at a certain height off the ground. Somehow you're able to measure the angle or something about the initial speed, and that's enough to help you answer all kinds of questions. What's the height, the maximum height the ball reached? If there's a fence, will it clear the fence? It's a typical question. Okay, a baseball 3 feet above the ground is hit with 100 feet per second as the initial velocity, and for some reason we're able to measure and say it's at an angle of 45 degrees. We can answer two questions. We can answer a lot of questions. Here's two that we're interested in. Well, what's the maximum height reached by the ball? And if the fence is 300 feet away and the fence is 10 feet tall, will it clear the fence? Okay, we can answer this question. The initial height is 3. Where the projectile is launched from, so that's h in our formulas. The initial speed is 100 feet per second. Notice our unit is in feet per second. So so anytime we see mag v naught, we'll put 100 in, and then 45 degrees. That's that's our pi over 4. So then because we're in feet, then we use the constant g to be 32. It's feet per second squared. That gravitational constant. So I can go right into my formula. My I and J components, I can plug in all these unknowns now. There's 3 unknowns, theta, mag v naught, and h. I plug them in. 100 times the cosine of 45, all of that times t. That's my I component of motion. 3 plus that same 100 now sine 45 times t, that whole thing. And then minus 1/2 gt squared. And of course, cosine of 45 is root 2 over 2. So although I don't have a calculator, I'm still able to get my hands on this because it used a reasonable angle and reasonable numbers. So 100 times root 2 over 2, will just give me 50 root 2. And that's times t. That's my I component. That's my horizontal motion expression. My vertical motion expression is that same 50 root 2 t, but then I have a 3 added to it. Then I have a minus 16t squared. And I can answer all my questions knowing those two formulas. Okay? The maximum height reached by the ball. Okay? When it reaches that maximum height, the velocity vector will have a 0j component. So the motion, we know the picture for the motion. At that maximum height, the velocity vector comes off tangent, and it's horizontal. It's parallel to the ground. And so we can use that aspect then to help us find out how long it takes to reach that maximum height. The j component of the velocity vector should be 0. So I just take the derivative. The derivative vector, this is my velocity vector. I take the derivative and I focus on the j component. It should be 0. So I set it equal to 0. It's tough because I don't have a calculator, but I can represent it at least in symbols as 25 root 2 all over 16. If I had a calculator, I would know that's about 2.21 seconds later. It's going to reach that maximum height. But my question says, find the maximum height. Not how long it took to get to that maximum height, but find the maximum height. You know how long it takes, so you take that t, use this version of it, and plug it into position. Okay. We don't really need the I component of it. I mean, we could get it. What we want is the y, how high off the ground it is. So we say that's going to be equal to 3. And then it simplifies nicely because of the root 2's and the 50's and everything. So I have 50 root 2 times t minus 16 times that t squared. Everything squares out nicely, and it actually ends up reasonable. So root 2 and root 2 is a 2. This 2 can cancel with this and give me an 8. And 50 and 25, I just have to take that. Here I have this being squared. So 25 squared being 625, and 16 squared. We can do that, basically. And to save ourselves some trouble, this 16 and this 16 squared can be a 16. And then this if we want to leave it as a 16 and not do this cancellation here, it's 100 times 25. 2 times 50 is 100 times the 25 if we don't want to do that cancellation so that everything is over 16. It's tough without a calculator, but it's what we have to do. And so if I have 2500 over 16 and I subtract 1250 over 16, I have 1250 over 16. And I add 3 to that. 1250 over 16, and I add 3 to that, or 1298 over 16. Three is 48 over 16. So 48 and 1250 is 1298. Okay, so 81 and an eighth. So 81 feet, 81.125 feet off the ground. 81 and an eighth. That's the maximum height reached by the ball. You can't use the symmetry because it's not launched from the ground. You can't just double the time to figure out, when does it get back to the ground. If you double the time, that's actually when it gets back to that height of 3 feet off the ground. Okay, so we need to see what's going on 300 feet from where we start at. That's an I component question. When we are 300 feet from where the ball was struck, we want to know how long it takes. The position I component is just 50 root 2 times t. And so we just set that equal to 300 and find out the time. Okay. 6 over root 2. 300 over 50 root 2 can cancel to be 6 over root 2 or 3 root 2 once you rationalize. We need this version of it, though, because we're going to plug it in and see at that instant in time, how high off the ground are we? Still position, not velocity. So 3 plus 50 times 3 root 2 minus 16 times 3 root 2 quantity squared. This is a nice thing we can actually calculate. This is 300, I believe, because it's It's 6 times 50. And then squaring this, we get 18. 18 times 16 is 288. So yeah, it's high enough. 303. Take away 288 is that it's, at that instant it's 15 feet off the ground. So yes, the fence is 10 feet off the ground. The ball is 15 feet off the ground. It's going to clear unless there's some fan that reaches over and grabs it. It's a home run. Okay, with no knowledge of physics whatsoever. Now, those of you who have these physics formulas imprinted into your brain, that's great. Right? Maximum height is this formula, which is wonderful. The key, though, in all those physics shortcut formulas is that it's launched from an initial height, 0. Launched from the ground. There's a formula for the flight time. There's a formula for the range, how, you know, the distance traveled horizontally. There's a formula for the maximum height. And I'm fine with you using that. Okay, max height, you can work your way through with max height. That's fine. But for flight time and range, you can't backtrack your way through using those formulas. Our book gives us these formulas. Only use them when you're launched from the ground. When you're launched from initial height, h equals 0. Definitely use them then. But if you're not launched from an initial height of 0, then I say don't use them. Okay. Here's a question that has us being launched from the ground. So we just use the physics formulas. You want to know max y? I plug into that formula, which I have on my cheat sheet. You want me to find the initial speed? I can figure that out because I can know the range of the ball. This is from our textbook, question number 23. If I know the range of the ball, I know the angle, alpha, and I'm launching from the ground, then that's enough for me to backtrack and figure out the initial speed of the ball. And then for that initial speed, I can find out how I could have done this, how I could reach, or how can I basically make a range 6 meters. What kind of angle do I launch at so that the ball lands 6 meters from where I start at? I can answer this question. I'll have 2 different angles to use. So just using the formulas that they give me, I can backtrack and solve for V naught. And I don't mind you doing that at all. Just cheat sheet formulas and solve the cheat sheet formulas. For that particular V naught and a different range with the same universal constant, go back and find out what the angle needs to be. And so the formula that uses that will be V naught squared over G times sine of twice alpha. Here's the issue though. When you set it up that way, the sine of twice alpha, you should use an identity to help you out. Okay? And so, or if you don't, you need to draw a triangle and figure it out. The sine of twice alpha is 6 over 10. So you can make a triangle, but that triangle is for alpha, not for twice alpha. And so you need to make a triangle and then still be able to decipher what twice alpha is. Okay, I don't know, call it omega or call it some other angle, beta. It should have a sine of 6 over 10. It's a 3, 4, 5 right triangle. So you can get the angle, I don't know, call it theta. But that's not the angle you're looking for. You're looking for twice that angle. So you have to divide that angle by 2. So it can work, and you can do it. And you can use those physics formulas. I don't mind it at all. Sorry I didn't write it all out. But that's perfectly fine. Just remember, though, you have to see this ground level for you to go launch into those formulas. Put them on your cheat sheet and use them when that's the case. Just know that everything won't be in that particular way. Sometimes we don't even know the angle. And so the next question looks at what do we do when we don't know the angle? Okay, so these general formulas are always true. And so anyway, okay, yeah, let's try to do this. So here are general, this is like a summary sheet here. Here are general formulas And if h is 0, go ahead and use those physics formulas. This is a summary sheet. I don't know if you have this even in your skeleton slides. Sorry. And then and here's a question that doesn't have any of this. This is from an old final exam question. See, we don't know the angle, but we do know something about that initial velocity. We know the I and J components of it. We know the horizontal velocity and the upward velocity. And that's enough for us to answer the question. I can't do it in 2 minutes. We should stop.